third type of induction problem, and that's one that involves inequalities. So proving an inequality via induction. Now, there is a common misconception out there that inequalities will only be asked in Extension 2 exams, and that's not true. It could be in Extension 1 as well. In fact, 2 years ago, I think it was 2 years ago, there was an HSC question, and it was an induction inequality, and there was all uproar, people kicking up a stick, going, oh, you can't ask that. And that's when people got the shock of their lives when they realised, oh, yes, you can. So you could appear this. So we're going to show that, or prove that 2 to the power of n is always greater than n squared, so long as n is greater than 4. So if n is greater than 4, my first case will be? 5. Very good. It's actually 5. It's going to be greater than 4. We're going to prove the result is true for n equals 5. So left-hand side, 2 to the power of 5, that's 32. Right-hand side, 5 squared, 25. Yes, 32 is certainly bigger than 25. So yes, it does work for our first case of 5. Going to assume the result's true for n equals k, where k is, again, we match the condition, so an integer greater than 4, or another way of saying that, greater than or equal to 5. So we're going to assume 2 to the power of k is greater than k squared, and we're going to prove the result's true for k plus 1, so 2 to the power of k plus 1 greater than k plus 1 squared. That's what we're trying to prove. Okay, so 2 to the power of k plus 1. So I've got to get my assumption in here somewhere. My assumption involved 2 to the power of k. So I'm going to rewrite 2 to the power of k plus 1 as 2 times 2 to the power of k. But we have assumed 2 to the power of k is greater than k squared. So therefore, that line will be greater than 2k squared. Okay. We're trying to get k plus 1 squared on the right-hand side. All right, well, if k plus 1 squared, but when I expand k plus 1 squared out, I get k squared plus 2k plus 1. That's what I'm trying to get on the right-hand side. So I'm going to split that 2k squared up to be k squared plus k squared. So I've got this k squared sitting there that I want, but I've got this other k squared that I don't need. K squared could be thought of as k times k. So I can now say that line is greater than k squared plus 4k. Because remember, in our assumption, we actually assumed two things. Not only did we assume that 2 to the power of k was greater than 2k squared, just k squared, we also assumed k was greater than 4. And that's the assumption that I'm using here. So k times k must be bigger than 4 times k. Okay? So I've used that part of my assumption. K is greater than 4. Remember what we're trying to get. We're trying to get k squared plus 2k plus 1. So I'm going to rewrite that. So I've got my k squared, I've got my 2k, but I've now got this extra 2k bit that I don't need. What I need is 1. I'm going to use the same sort of idea. That's got to be greater than k squared plus 2k plus 8, because k is greater than 4. Now, last time I checked, 8 is bigger than 1. So if I've got k squared plus 2k plus 8, and it's bigger than that, well, it's certainly bigger than k squared plus 2k plus 1. And of course, that equals k plus 1 squared. And so I now have the result that I'm looking for. So yes, indeed, 2 to the power of k plus 1 is greater than k plus 1 squared. Now, be careful with your notation as you're going down. Notice I'm saying this line is greater than the next line, or I'm saying this line is equal to the next line. So as I'm reading down, I'm saying 2 to the power of k plus 1 is equal to this line, which is greater than this line, which is equal to this line, which is equal to this one, but that's greater than this one. Equal, greater, greater, equal. So therefore, the whole thing is greater. The one thing I must do when I'm going down, if I use an inequality sign, I've got to use the same one all the way down. Because as soon as if I was to write a line down now that said, oh, this is less than something, now my proof's no good, because I'm saying this is bigger than this line, which is less than this line, and I've lost the whole thing. Hence, true for k plus 1 if also true for k. And now I will induce, but remember, my first case was not 1. So since the result's true for n equals 5, then the result is true for all values of n greater than 4, or if you like, you could put greater than or equal to 5 by induction if you can find the right font and the symbol that you need to use. Alrighty, so there's just a couple more questions. Those ones involve inequalities that we'll have a look at.